Hi, welcome to this video on how to approximate the value of pi using your calculator. Now, you might already be aware that on your calculator you can obviously put in the value of pi and you'll get a number out. But I feel that's kind of cheating. In this video, we're not going to use any trig functions that are available on your calculator. We're going to use the square root, and that's pretty much the most complicated function that we're going to use. Everything else is very sort of vanilla, if you like. We'll cube stuff, square stuff, add stuff, pretty much it. But by the end of it, we're going to have a pretty good approximation of pi. So let's get an idea of what we're going to do. So we're first going to understand the expansion of arctan. That's the Taylor expansion of arctan. We're then going to form an idea on how we can manipulate this to find a good approximation of pi. Then we're going to move on to step 2, where we actually carry out this. We're going to create a recurrence relation using an arctan identity. We're going to use this recurrence relation to find a substitution that we can put into our Taylor expansion. And this is going to give us a very accurate value of pi. Now, you might know already that arctan of 1 is equal to pi on 4. And this is what we're going to be aiming to manipulate. So let's have a look at a graph and see why using arctan of 1 would be a bad way of approximating. So what I've got up here is a Taylor expansion of arctan. I've only done it for 3 terms. So we've got the 0th, the 1st, and the 2nd term. But as you'll see, this approximation is pretty good when we have a value very close to 0. If we were to zoom in, you can't really see the difference between the blue and the red line. So what we want to do, instead of using arctan of 1, where if we scroll all this way out, we see there's a sort of a big gap between our Taylor expansion and the red line. Instead of using arctan of 1, what we're going to do is we're going to use an arctan formula to try express arctan of 1 in terms of arctan of smaller numbers. By doing this, we're then going to hopefully make use of the error here, where there's practically no error. Or the error that there is so small that it's not really going to be important for us to look at. Also, when we decide to sort of expand this up, if we wanted to find more decimal places of pi, we would then be able to just increase this expansion, so to say 10, which by the way, still is not very accurate for 1. And we'll be able to do our recurrence relation, which we'll see later on for more terms. So let's have a look at forming our recurrence relation. Hi, so let's now derive a identity involving arctan. So what I've done here is I've wrote that tan A plus B equals tan A plus tan B, blah, blah, blah. It's just the additional formula for tan. And then I've defined alpha and beta to be this. Next, what we're going to do, we're going to take equation 1, and we're going to do arctan to both sides. That's going to cancel the tan on the left side. So we're going to be left with A plus B, which is equal to arctan of tan A plus tan B over 1 minus tan A tan B. Now, instead of writing A plus B, we can replace it now with its definition in terms of arctan of alpha. So arctan of alpha plus arctan of beta. And that's equal to arctan of, well, tan A is alpha, tan B is beta, and that leaves us with this formula, identity. Now our goal is to make use of arctan of 1. But we saw that using the Taylor expansion, this minus 1 to the n x to the 2n plus 1 over 2n plus 1, we saw that this would be very inaccurate for small values of n when we're dealing with x equals 1. But if x is closer to 0, then this will be very accurate. So our goal is, using this arctan identity, we're going to try convert arctan of 1 into arctan of something plus something. More precisely, I'm going to let these two somethings be equal to each other. So we're going to rewrite it as 2 arctan of something. Well, that means we want to kind of form a recurrence relation. We want to write arctan of xn as 2 times arctan of xn plus 1. Now that means alpha and beta are equal to xn plus 1. So we have the arctan, where we're using now this identity up here, arctan of xn plus 1 plus xn plus 1, so 2xn plus 1, divided by 1 minus xn plus 1 times xn plus 1, so xn plus 1 squared, is equal to arctan of xn. Here's where we're going to get our recurrence relation. We really want xn plus 1 equals something in terms of xn. So I'm going to do inverse arctan. So I'm going to take tan on both sides. That's going to give me xn equals 2xn plus 1 over 1 minus xn plus 1 squared. Now I'm going to cancel the fraction. So that's going to give me xn minus xn plus 1 squared, where all I've done is I've multiplied by the denominator. Next I'm going to divide by xn, so I get 1 minus xn plus 1 squared equals 2 over xn plus 1, and this is like a quadratic in terms of xn plus 1. So we get xn plus 1 squared plus 2 over xn plus 1 minus 1 equals 0. Solving this, and we're going to take the positive solution of our quadratic. Doesn't particularly matter, but because our initial value is the positive one, it makes sense to take the positive. However, it doesn't particularly matter. So xn plus 1 is equal to minus b plus square root of b squared minus 4ac divided by 2a. This simplifies to become the square root of 1 over xn squared plus 1 minus 1 over xn, and simplifying all of this we get the recurrence relation xn plus 1 equals the square root of 1 plus xn squared minus 1 over xn, like this. And remember, this is going to determine our coefficients. So we had the x0 is equal to 1. So let's calculate some of the x terms. So I'm going to do this by calculator. So I'm going to enter 1, I'm going to select equals. I'm then going to write square root of answer squared plus 1 minus 1 all divided by answer. So what you want in your calculator is something like this. Then if we click once, we're going to find x1. That's minus 1 plus root 2. If we click twice, we're going to find 0.1989112, blah, blah. If we click again, we're going to get 0.98 or 0.098, blah, blah. x4 is going to be 0.0491, etc. x5, and x6 I've got to be 0.01227,246. So how can we then use this to calculate arctan of 1? So we know that arctan of 1 is the same as arctan of x0, which is equal to 2 times arctan of x1, which is equal to 4 times arctan of x2, blah blah blah. This is going to be 2 to the power of 6 arctan of x6. So next, let's now involve our Taylor series at the top. So we know that pi on 4 equals arctan of 1, which is equal to, replacing this, we have 2 to the power of 6 times what's going to be x6 minus x6 cubed over 3, etc. And plugging that into the calculator, we get 2 to the power of 6 times answer minus answer cubed over 3, which gives us 0.78539. Actually, I'll add on a few more digits. 0.753981598. So pi is this number multiplied by 4. And we do in fact get 3.141592639, which is pretty close to pi. You'll see that this digit is correct, these digits are correct, these digits are correct, and this one's correct. But unfortunately, these two fail. But nevertheless, all we've done is using quadratics and a recurrence relation, we've found the value of pi to pretty good accuracy. Now, I don't mind making another video on this where we use Python to, find pi up to the first million digits. So if you're interested in that, please let me know in the comments and I'll get making it.